Hello everybody. In our previous lecture, we have seen that how Boolean algebra, its theorems can be used to minimize or to simplify a Boolean expression. And we also understand that simplifying a Boolean expression is very important from the cost perspective. So, and we have also seen that if we use Boolean algebra, so we have observed that there is no systematic procedure. So for example, if we want to reduce number of terms, so there were four steps suggested. We can use uniting theorem, you can use consensus theorem to remove literals, to remove terms, and along with that some other methods were suggested that we can use we can add additional terms, redundant terms, so that we can reduce some other terms. So which steps need to be performed and in which order, this is a complex problem, and there is no known solution. There is no working solution which can tell you that okay, you have to first apply this step, then go to this step, and then go to this step. And unfortunately, what happens that if you go with a different order of steps, sometime different optimized expression comes out. So what we need if we want to minimize a Boolean expression, then we require a systematic or procedural approach. Systematic means that there should be only one solution, and procedural means that we can follow some steps. Step number 1, step number 2, step number 3, and then finally we'll come up with a definitive solution. Okay, so this systematic and procedural solution will in this lecture we'll start understanding how that systematic and procedural approach will work. So the first step in that procedural approach is first we convert the Boolean function or Boolean expression into canonical form or standard form, and then we go ahead and minimize that expression. So let's again understand why minimization is important. So we have seen that if we have less number of terms, that certainly reduces the number of gates. That means it would reduce the cost. And also if we reduce the number of literals in each term, that would reduce the number of inputs in each gate, and that would also affect in reducing the cost, as well as the performance will also improve. Performance means the overall latency of that function, overall delay of that function will also reduce. So with that goal, we'll first try to see the systematic approach. In the systematic approach, first we will understand what is a canonical or a standard form. So to see this reason, or like why do we require a standard or canonical form. So in last two lectures we have seen there are several equivalent Boolean expressions. So that essentially means that one Boolean expression, let's say a plus b plus c, there could be many different forms in which we can represent the same expression. And unless we know that what that expression, whether that expression are equivalent to this original or given question, so whether they are same or not, it again is an effort to know whether two expressions are same or not. The only method which will always work when we are comparing two expressions, whether they are same or not, is to write truth table of both these expressions and then match each and every row of the truth table. If they are matching, then we can say that they are same, otherwise we cannot say. So because even matching two expressions, whether they are equivalent or not, is a tedious process. So that is why we would require one canonical or a standard expression or standard form in which a function can be represented. So this example is given like a plus b plus c. You can see that I can also write this a plus b plus c equal to a plus bc dash plus bc plus b dash c. or I can also write it like AB plus AB dash plus A dash B plus AC plus C. So there are various other, and you can take it as an exercise that whether all of these are equivalent or not. You will finally see that yes, they are actually. And using some of the theorems which you have studied, we can use those theorems to understand, to see whether we can check equivalency based on those theorems. However, sometimes those theorems are not sufficient because, as I said earlier, that you have to perform steps in certain order, and that order is sort of undefined. So that's why if there is some canonical or a standard representation, that means that given an expression, first we go ahead and represent that expression in a canonical form, and from that canonical form, because that's going to be only one canonical form, from there we start and then we minimize. So there are two canonical forms which we have seen, which we will see in this lecture. One is called sum of product and another is product of sum. So canonical sum of product form. So here each term, so you see how many terms would be there? There would be product of sum of product. So that means one term is a product term. So in each product term, if there are n variables, all the variables should be present in each term, either in the normal form or in the complemented form. So in other words, if there are n parameters or n variables in that function, then each term will have n literals. Literal mean either that would be present in the normal or original form or in the complemented form. So there has to be n literals in each product term. So for example, in this case, I see that there are three variables, a plus b plus c. That means there has to be at least three variables. So in this this is also a product, a sum of product. So in sum of product, this product term has only one literal, and this product term has only two literals. So here also, here the literals are variables. So these are two literals in each of the product term, and this particular term has only one literal. Although in the last one, you see each of the product term has three literals, or essentially all the three input variables are present in each product term. So a b c dash, a b dash c, a b dash c dash, a dash b c, a dash b dash c, a dash b c dash. So all the product terms have all the three variables, either in the complemented form or the normal form. So this would be the canonical form of the sum of the product expression. So this is in other words, they are sometimes called standard SOP, standard sum of the product form of that particular function. So now this is clear that in a canonical form, in each product term there has to be all the literals or all the variables present. And the second thing is that all of these product terms are also called mean terms. Okay, and if we see, this is sort of a representation of your truth table. So for example, in your truth table, wherever you have a 1 as an output, you one product term would be corresponding to that particular one. And so let's understand this mean term thing and also this truth table with help of an example. So let us say we have this function ab plus c. It has three variables, a, b and c. Now if I want to have this canonical representation, so then each product term has to have all the variables. So what I will do is I'll multiply ab with 1, and 1 also means c plus c dash. So I am multiplying ab with c plus c dash, and I am multiplying c with a plus a dash and b plus b dash. So the overall idea is so that I can have all the variables in each product term. Now I can multiply this AB with C and AB with C dash, and similarly I will multiply this whole expression. then the expression which will come out is the expression which will come out would be like this. I have started with this a dash, yeah, so I have first opened up this one. So this is a dash b dash c, a b dash c, a dash b c, a b c dash a b c. So there were 2 times this ABC was generated, so I have removed one of that ABC. So essentially there would be 5 product terms. So when if I write the truth table of this expression AB plus C, it will come out to be something like this, that first I will enumerate all the options of ABC 0 0 0 0 0 1 up to 1 1 1, and then for each input sequence I will find out the value of f by applying that AB plus C. So essentially A and B, both of them has to be 1 or C has to be 1, then f would be 1. So f is 1 because C is 1 here, and if C is 1 then it is 1. C is 1, so it is 1, but both A and B were not 1, so that's why it was not 1 here, it was all 0. So when A and B both are 1 but C was 0, then also it is 1 because at least A and B both are 1. So similarly this is the truth table. So if we try to find the correspondence of this sum of product term with this table of truth table, so you will see that each of this term corresponds to a row of this truth table wherever output is 1. So for example, this here, this I can say A, when A dash, so when A is 0, that means A dash is 1, and B is 0 means B dash is 1, and C is 1, then only this particular output would be 1. So this is corresponding to one mean term, which is A dash B dash C. So in other words, this particular mean term A dash B dash C would mean that only this particular term, so let's say in a function only this term is there, A dash B dash C. So that means in my output only this particular for this particular input combination output would be 1, and for all other cases output has to be 0. Okay, so this is also the reason it is called mean term. So this is the minimum terms that has to be minimum term to represent this particular function. So if only one value is 1. So now another way to look at this whole thing is that wherever 1 is there, if corresponding mean term, corresponding value of A and B, A, B and C is written here, so that would I can use all of those 1 terms and say that if any of those 1 terms, any of those mean terms is 1, then my function f would be 1. So this is another way of looking at sum of product expression. So here let us see the mean terms corresponding to all of these A, B, C. So for example, this row corresponds to A dash, B dash, C dash. So if this particular mean term is 1, so that means my A dash, my value of A is 0, B is 0, C is 0, then only expression will give me 1. So then this particular mean term has to be 1 or has to be present in my canonical form. So here A dash B dash C is present, so I am making it red, and I am calling this mean term as M1. So these are represented using decimal numbers. Okay, so they are not represented using binary numbers but decimal numbers. This represents 0 because 0 0 0 is 0 and 0 0 1 is 1 in decimal, so we are writing it as small m, means mean term 1. So similarly A dash BC, this particular term, so A dash BC is another mean term which is present. A dash means A is when value of A is 0, when value of B is 1, C is 1, then this particular mean term will become 1. So similarly we can see all other mean terms which are present here. So the overall sense we have to make out of this mean term as well as the correspondence with truth table, that when any of these mean term is 1, then my expression is true. Okay, so each mean term represents to 1 in the truth table. So the whole expression, that's why in a canonical form we can also write it like a function. This f is equal to mean term 1 plus mean term 3 plus mean term 5 plus mean term 6 plus mean term 7. So rather than writing in this long form, we can write directly the corresponding decimal number for that mean term. Now further, for expressing this or for writing this, we also sometimes write the expression, this is the symbol of sum, and m, we are using this parenthesis m, and using this parenthesis means this is m1, m3, m5, m6 and m7, and because of sum, we are sum symbol, we are adding all of these mean terms. So this function f in a canonical or a standard SOP form can be represented like this, which is also equivalent to expressing it in terms of variables like this. Okay, so this is one of the canonical form, which is sum of the product. Similarly, the other canonical form is called product of sum. So it is the dual nature of Boolean expression, that anything which can be represented as sum can also be represented as a product. So here we have product of sum, means each sum would be considered as one term, and because it's a canonical in nature or standard in nature, so each sum term should have all the variables present either in the normal form or in the complemented form. And like sum of product, here also each sum term should have n literals. Okay, and these sum terms are called max terms, and each of these max terms represent one row of the truth table wherever output is 0. So let us see again with an example. So I am taking a very similar example. Let's say a function ABC is represented in form of a product of sum, where a plus b is one sum term and c is another sum term. So if I want to create a canonical form, then the idea would be that first of all I have to add there should be all the variables present in each of the sum term. So here c was not present, so I created a plus b plus 0, and 0 can also be written as c dash, because I wanted in each of the sum term there has to be c and c dash, both the terms. And similarly here in this sum term, a and b both has to be there, so I added a dash plus b dash, both of them are effectively 0. So by expanding this expression, we can see what would be there. So using the distributive law, a plus b plus c and a plus b plus c dash, and similarly if we expand this whole form, then it will be a plus b plus c, a plus b dash plus c, a dash plus b plus c, a dash plus b dash plus c. Now we see ABC appears twice here, so we can remove one of the which is redundant. So again, if I would create the truth table for this particular expression, then a truth table will come out something like this. So my output is 1 when both this expression a plus b is 1 and c is 1. So whenever c is 1 and either of a and b is 1, then the output is 1. Similarly, either of a and b is 1 and c is 1, then the expression is 1. here also, when both a and either a and b is 1 and c is 1, then the expression is 1. So a max term actually would represent a 0 in each of this expression, in each row of the truth table. So for example, if I have a plus b plus c, so I will write it like this. If corresponding to this row, if we have this particular term, this particular sum term, a plus b plus c, what is the result of that? That means that only in this particular row it would be 0, in rest of the rows it would be 1. Okay, so similarly, if a plus b plus c dash is the sum term, that means it would be 0 here and would be 1 in a rest of the rows. So similarly, we can find out the sum expression corresponding to each row, and then we can also represent it using a decimal number 0, 1, 2, 3, 4, 5, 6, 7. Now so we have created a sum term corresponding to each row. So this particular sum term corresponding to each row is called max term, because in that case only 0 is present in that row, and in rest of the cases, in rest of the rows, 1 is there as the output. So it's also called max term. So it's just terminology, you can see it that way. Okay, so the whole expression can be written as that if it's a product of all 0 terms, so that means when any of those term is 0, the whole expression would be 0. Or in other words, all these sum expressions has to be false to make the whole f as as 1. So I'll repeat. So let us say I have product of sum. So each of the sum term, when each of the sum term, any of the sum term is present, that means that particular sum term will make the whole expression as 0. Or to make that function 1, none of the sum term has to be 0. Okay, so that means the only remaining part, so the terms which are not present here, any of them is there, then only this function f will become 1. So this is how product of sum expression will form a canonical form. And now for this particular function a plus b into c, we see these max terms being present, m0, m1, m2, m4 and m6. So we can say that my function f can be written as product of m0, m1, m2, m4 and m6. So what does this mean? This means that when any of these terms are present, then my output would be, when any of these m terms are present, then my output would be 0, else my output is going to be 1. Okay, so because it's a product term, so I can write this as a product, and then m, capital M means max term. So max term 0, 1, 2, 4 and 6 are being multiplied, so that I can get this expression f. So this is how canonical form of product of sum can be written or can be derived out of any expression. So now there is also a couple of relations. So there is some relation between product of sum and sum of product form. So looking at this also, we can say that because all zeros are represented by a product of sum, while each one means it's a mean term. So we can say that whenever, so they're complementary in nature. So that means if a function f is represented like this, 0, 1, 2, 4, 6, actually this function 0, 1, 2, 4, 6, then this can also be represented using sum of product term 3, product term 5 and product term 7. So I can say that these two are equivalent expression. And the other relation between this mean term and max term is that because of De Morgan's law means if I want to complement a function, so let's say f is a function where f is a function of mean terms, sum of mean terms 3, 5 and 7, then I can say that f dash, in f dash all these 3, 5 and 7 would be 0 and all rest of them would be 1. So I can also say that f dash is actually product of max term 3, 5 and 7. So we can look at algebraically also. In algebraically, if I want to write sum of 3, 5, 7, it would be written as a dash b c plus a b dash c plus a b c. Now if I want to apply De Morgan's law, what De Morgan's law says that every product will become sum and every sum will become product, and the polarity of each variable would be inverted. So a dash become a, b become b dash, c become c dash, and this all the product things will become sum. So similar for all of these product terms, they become sum terms, and this sum term, this product term also become the sum term. So if I see this corresponds to 0, 1, 1, that means 3, and this is 1, 0, 1, that means 5, and this is 1, 1, 1, that means 7. So algebraically also we can see that De Morgan's law can be applicable here for the mean terms and max terms, and this also gives us some sort of a shortcut. So we can see that if something can be represented efficiently in mean term, we can use that particular approach, or something which can be represented using max term, that can be followed. So after arriving at the canonical form, the next step we wanted to see is that after having the whole expanded form where all the variables are present in each of the sum term or a product term, then how can we further minimize? Okay, so the further minimization can be done by using can be done by using uniting theorem. So in this uniting theorem, so there is only one theorem that could be sufficient here. We just need to see that which variables we need to combine. So now the uniting theorem says that xy plus xy dash is equal to x, and for product of sum it is x plus y plus into x plus y dash equal to x. So this uniting theorem can be applied multiple times, can be applied again and again to reach to a final solution. So only one theorem is sufficient to simplify the expression. Okay, so I'm giving various examples of this uniting theorem. So let's say y plus y dash equal to 1, because both can be combined and will become 1. So similarly xy dash x dash y plus x dash y dash will become 1. So essentially I can say that xy dash plus xy, this will become x, and similarly x dash y plus x dash y dash will become x dash, and x plus x dash will become 1. So we can apply that recursively. In other words, if all the four combinations of my truth table 0 0 0 1 1 1 1 0 0 1 and 0 0, if all of the four are present, then I can say that the expression is always 1. So let's say if the expression is like this: xyz xy dash z x dash yz x dash y dash z. So I can take z common, and then I can, using this particular the above expression, I can remove all the xy terms, and the term final output would be z. So this way only the uniting theorem is sufficient. It could be applied in different scenarios and different combinations that could help us in receiving or getting what could be the minimum expressions for minimum expression for that particular combination. So one more question here, that let us say a particular so all of this expressions, all of this like mean terms and max terms, they depend on creating sort of a truth table where we know for each input combination what is the output. What if certain input combinations are not there, or their result is not known? Or so there are two possibilities. One, that we don't know what are the results. The second is that those input combinations will never occur. So in those cases, it doesn't matter what are the output for those combinations, those input combinations. In such cases, we call such functions or such expressions as incompletely specified functions. And those input combinations where output is not known, or those input combinations which will never occur, are called don't cares. So these don't cares are written like let's say in case of sum of products, it's called let's say M1, 2, 3 and 6. Then we can say that plus sum of don't cares 7. And the same expression, if you want to write it as product of sum, then it would be product term max term 4, max term 5 plus don't care 7. So this way, these don't cares or these incompletely specified functions can also help us further to optimize. So we can use these don't care terms to further simplify our expressions. So we'll see how these things can be done. So now we have already seen that how we can use this uniting theorem. Now the better or a systematic way, because as human beings, rather than working with numbers, we are very comfortable seeing things visually, creating patterns and identifying patterns. So that is why one popular approach for Boolean simplification or Boolean expression simplification is called Carnot map. So this Carnot map is essentially a visual solution where we represent all the mean terms and max terms in form of a 2D or 3D diagram, where there would be multiple cells. Each cell corresponds to one mean term or max term. So either it has a mean term or max term. So let's say we are simplifying for sum of products, then we will only use mean terms, not max terms. So each cell in my Carnot map would represent one mean term, and the other property of this Carnot map is the adjacent cell vary or differ only in one variable. So for let's say my Carnot map is for 3 variables, the rest of the 2 variables would be same for each adjacent cell, and only one variable will change. So because there is going to be only one variable change, so the way these Carnot maps are represented, their form of they are represented rather than decimal, but in a gray code encoding. So let's take a quick example of how these Carnot maps are represented. So let us say I have these 3 variables. So for 3 variables, let's say variables are A, B and C, and A being we are keeping A at the most significant place and C at the least significant place. So I can write it like 0, 1. So this is a gray code representation: 0, 1, 3, 2, 4, 5, 7, 6. So if it is a 4 variable, so it would be like 0, 1, 3, 2, 4, 5, 7, 6, then 12, 13, 15, 14, 8, 9, 11, 10. So I think the next slide will make it more clear. So here it would be written like this. So you see that this particular cell represent mean term 0. Or it is also saying this is A dash, B dash and C dash, and this particular cell says this is A means it is 1, and B dash C dash are in complemented form, that means they represent 0. So this is 1 0 0, and this particular cell, my value of A most significant is 0, and then B is also 0, and C it is 1. So this represent mean term 1. Similarly, this represent mean term 2 and this represent mean term 3. So we can see this is actually a gray code where adjacent cells have only a bit flip at one place. So here there is a bit flip at this second place, and here we see the bit flip is only at the least significant bit. Okay, so similarly, for variable k map can also be represented using this. So I can have two variables on this axis, x-axis, and two variables on y-axis, and they are also represented in a gray code manner. So a dash b dash, a dash b, a b, and a b dash. So writing it this way, like writing a dash b dash or a dash b, so this help us in writing this k map in a more precise manner. But otherwise we can also remember these numbers if we want, 0 1 3 2 4 5 7 6, etc. So so once they are, here you see there are a couple of things. One, that each of the cell represent one of the mean terms. So whatever number was written here, 0 1 3 2, they are representing mean terms, and they can also represent max term. So in case of max term, we have to remove this a dash b dash, we have to write it like a plus b, and this we have to write c plus d. So this can also be represented as max term. The numbers of max term will again remain same, but in that case my result would be in terms of product of sum. So each cell represent one of the mean term or max term, and adjacent terms, adjacent cells are differed only by one bit. So essentially all the adjacent cells can be united. We can use our uniting theorem to combine each adjacent cell. Now adjacent cell could be in x direction, it could be y direction. So basically it could be adjacent horizontally, it could be adjacent vertically, it cannot be adjacent diagonally. So diagonal cells does not have any kind of a correlation, but the last row and the first row and the last row, or the first column and the last column can also be combined. So you see in this first cell and this is the last cell, here also the difference of bit is only 1. So this cell is the last one, this is the first one. Here also the bit difference is only at 1 bit level. So it's a kind of a rotatory in nature. So adjacency could be adjacent cell, and even if it is a like it could be coming from the top, or basically it could be a rotation based adjacency. The number of cells which could be combined, it could be 2, it could be 4, it could be 8. So any power of 2, those, if we find a group of them forming a rectangle or a square, we can use all of them to combine. Okay, so we'll see all of these k maps with help of couple of examples, and these examples we will I will use the writing pad so that we can you can also see that how to solve these examples. So and that part would be seen in the next part. So this lecture would be divided into two different parts. So one part is this, where we have explained, or we have summarized how to create a canonical form and how to create a k map. So the next part of this lecture will take couple of examples where k map could be various example of k map could be taken, where optimizations, or how we can form this group, and how we can simplify using k map. Thank you very much.